All right. Hello, everybody. Um, let's see. Is this on? Okay. I suppose this is as good as we can get it. We have markers, plenty of. We have water. Right. So let's continue our conversation with the probabilities chapter. And today we're going to cover continuous random variable, which is the second part of chapter 3 as I defined it. So continuous random variable. Continuous random variable. So if we look at continuous random variable, random variables we have covered, and we have a vague understanding of what they do. Now let's look at the continuous part. The continuous part, the continuous part means we have a lot of possible values for a random variable, where when it was discrete there was a defined finite number of values. In a case of a continuous, there's a lot of possibilities. Those aren't necessary variables that the random variable is going to take, but it can manifest as. So we should start with the first important part, saying that if CRV, continuous random variable, that's this, has a symmetric bell shape curve, right? We describe it as having a normal distribution. So if we look at a continuous random variable and we start mapping it out in a graphical form, and it end up looking kind of a bell-shaped symmetric, so that, but also this, right? And let's see what we have or completely kind of flattish, that. Ooh. And the breeze is nice, right? So either one of those will be symmetric bell shape. So that's, but before we start talking about this, well, apparently today is Scooter Gang Day. But before we start talking this, let's talk about the most basic of the distributions we can encounter, and that's the uniform. The uniform distribution. And a uniform distribution looks something like that. And what does this mean? Well, it means that if we have our values for the random variable on the x-axis, we have our probability of each one of those variable on the y-axis. And in a uniform distribution, all values have the same probability of occurring. right, which lends itself to this shape, because regardless of which one of those we pick, called x1 and x2, probability of the first one, probability of the second time are equal. Oh, sorry, I forgot that. Wrong way. Right, so probability of the first one equals the probability of the second one. So that's uniform distribution. Right. There's some cool things we can do with it. Let's get out. There. There's some cool things we can do with it. Well, one cool thing we can do is that if we considered, here comes the game with the wind. One thing we can do is we can consider finding a grain of rice. So I'm assuming most of you are aware of the fact that rice can, and sometimes, a lot of the times, comes in those really big bags. And we're talking those 25-pound bags. So if we have a 25-pound bag of rice, and don't ask me if it's one of those short stem, long stem rices. I don't know the difference. I mean, when I see it, it's different. But so we're just talking rice, white little grains. And I took out one of the grains, and I made it black. So this is one special grain, painted black. And I took this grain and I tossed it inside of the bag of rice, 25-pound bag of rice. What's the probability that you're gonna pick the black grain of rice? Or conversely, what's the probability you're gonna pick a white grain of rice? Well, if you are supposed to reach with a pair of chopsticks or tweezers or with your two fingers, if you're into the bag, mix it up and pick up a grain, what are the chances you're gonna pick the black grain of rice? 0. And by the complement of it, picking a white grain of rice would be probability 1, right? So having the exact probability becomes difficult. So if we consider the bag of rice looking like this, and inside of the bag we have arranged all the grains of rice, right? Each between 0 and how big are those bags? 100 centimeters. Let's call it 25 inches. So this bag, right, has a height of 25 inches. So, right. So if I was going to slice it up, right, each one of those slices will be responsible for each one of the grains of rice. So what are the chances I'm going to pick a single grain of rice? Say the black grain is right here. And this grain is located exactly 13.00007 inches inside of the bag. The probability of picking a single value out of a continuous random variable spectrum, right? The probability for this is 0, right? And again, if in your mind 25-pound bag of rice is not big enough, then let's use a tractor trailer or one of those tanker ships, or containers of rice, of all the rice in the world. I mean, eventually you're going to get to the point where this is one option out of something that starts getting into infinity, right? So if we look at the probability of a single value in a continuous random variable spectrum, that's 0. Again, a very simple exercise to get comfortable with this idea of how many choices there are is to pick a number. Pick a number between 0 and 10. Say we're going to pick up 2. Pick a number between 0 and 2. Let's say 1. Pick a number between 0 and 1. Well, we're going to pick half. Pick a number between 0 and half. 0.1, right? Pick a number between 0 and 0.1. 0.007, right? Pick a number between those two. 0.00013, right? And so on and so forth. When will this game end? Well, when somebody decides to put so many zeros in them that you won't have a hard time dealing with it. Well, what's the meaning of this? Well, the meaning is that the amount of choices I have between 0 and 10 is infinite. You have infinite number of numbers between 0 and 10. So continuous random variable behaves the same way. Now, in case of rice, those pieces of rice are countable, but big enough that we can feign a feeling of infinite. Now, that doesn't have to be necessarily it, but you can pick any other example. N times for classes. The class is supposed to end at 80 minutes in. So what are the chances we're going to finish at any other time rather than 80 minutes? Right? And pick and choose. There's a lot of options for that. So I pick a grain of rice because that at least seemed to work as a visual cue. All right, so we have this one thing. On the other hand, if I kept on picking all the random variables up to here, what are the chances I'm gonna find the black grain of rice? So what's the probability of all grains? I mean, I'm gonna keep on picking out of the bag till there's nothing else in the bag. Well, the probability after you picking all the grains is 1, right? Because eventually you're going to find the black grain of rice. If the probability for the whole thing is 1, wouldn't it be cool if we could somehow visualize it? Say, what's the probability of getting a black grain of rice? So probability of black grain after picking up 50% of the bag. Right, so I take this bag of mine and I say, hey, I want to pick this half. I want to pick this half. What's the probability I'm going to hit the black grain of rice? Well, if I pick half of the bag, the probability should be 50%. So if we consider this, and this being 25 inches long, if we consider this being the bag of rice, right, then I cannot do probabilities for very specific numbers, but I could start doing probabilities for those sections of it. Well, to do that, I would like to make sure that this visualization makes sense, which means that I have to force the area here to be 1. Because if the area of this is 1, then picking everything from here to here, right, falls into this category of having the whole thing. So if this area has to be 1 and the length of this is 25, then what's the height needs to be? That's the height, right? 25 times 4%, right? 0.4, 0.04, yeah, 0.0. This makes the area to 1, right? Because area is height times width, which in our case is 0.04 times 25, and that equals to 1. And suddenly, I can have a conversation about it. Suddenly, I could ask a question, what's the probability of finding the black grain of rice if I pick anything between 2 and say 5 inches? Well, between 2 and 5, so this is 12. Say about here. What's the probability of this area? Because this was asking, it's asking about between 2 and 5. Well, the probability of this is the area covered. Because if the area is 1, right, then we can, right, say probability and area are behaving the same way. So what's this? Well, the length here is 3, right? 5 minus 2 as the width, and 1 times height. What height is still the same. So this is equal to 3 times 0.04. So that comes out to be 0.12, which is 12%. Okay. And suddenly we can talk about things like this just by using this very simple kind of connection. Because all we want to do in using the uniform distribution is get us used to the fact that if area equals to 1, right? If we can make area equals to 1, and the height of the box between 0 and 1, then what? Then we can start looking at probabilities as a visual representation of probabilities. Again, assuming uniform distribution. This is the important part, right? So now let's talk about this single value thing that we were talking about. So now questions. Let's go back to my 13 inches. So what's the probability, right, of finding a block of rice if we have this 13? Well, let's see. This is going to be this 13, so about here. Well, height of this is still 0.04. What's the width of it? Mathematically, a line has no width because it's a two-dimensional structure. So that means 0. which means that the probability of x equals to 13 is 0. Now again, in real life scenario using a bag of rice, that is almost 0, it's not exactly 0. But mathematically, when we're talking about a continuous random variable, it is 0. Line doesn't have a width. On the other hand, well, how about two lines? How about, probability when x equals 12 and x equals 13, right? Let's call it OR, one or the other. Well, again, the thickness of this line 0, thickness of this line 0. But if we decide to say, hey, how about x between those two values? This. Now we have something different, because the width of that is 1 and the height of this is 0.04, which ends up being 4%. So that's the basic idea about continuous random variable in a uniform distribution. Okay, if a problem arises, I hope you let me know eventually. Nobody has been talking to me lately, so I'm assuming everybody's on track. Alright, so what do we do next? Well, next, let's look at the normal distribution. Alright, this is cool. At least I think this is cool. And the cool part about it is, well, here's a normal distribution. And here's a normal distribution. Uh-oh. This means that I need to come up with this kind of area probability scheme for both of those. And there's some trickiness to it. For example, this has a smaller standard deviation. This has a larger standard deviation. Why? Well, because this one is less spread out. It's more in the center. This one's kind of blob all over the place, right? This has a smaller mean. This has a larger mean if they're on the same scale. What happens if they're not? What happens if one is in inches, one is in pounds, right? So we have to find the formula for each one of those, and then we have to slice it out. It just gets, I understand you guys want to do mathematics and you love mathematics and you want to spend the rest of the week, just doing equations and fighting with it, and I don't. And most people don't either. So what would be really freaking cool if we could take all of that, all of it, and ready for it, and force it to a standard normal distribution or curve. If we could take all of those different things and just put them into the mode. Now, why we want to do this? Well, because if we are forcing all of those curves to look and behave like this curve, then we can make this curve anything we want. Think of the military, right? They take any person. They take people that want to be there, they don't want to be there, people that are schmucks, people that aren't schmucks, and make soldiers out of all of them. With, more or less a good success rate. But the idea of it is, right, that it will be really cool. Why? Because we can put conditions on it. For example, me personally, I'm tired of seeing standard deviations being 1.724. Because doing any kind of, is it usual and unusual, requires to calculate things, and I just don't want to. So how about we force this distribution to have a standard deviation of 1? While we're at it, wouldn't it be really cool if the mean was just 0? This way you know for a fact if something is greater than the mean by just seeing if it's positive, and negative means smaller than the mean. It just makes sense. And lastly, and most importantly, how about we force this whole area, right, of this wide curve to just be 1? Because if we can force the area of this 1 to be 1, we can talk about the probability as well in the same sense. Sorry. Right. So this would be really cool if we could do this. Well, we can. And there's a special function that we use that takes all these really weird distributions, normal distributions, and force them to be normal. And I know you didn't see it before, so... Oh, now you saw it. It's z-score. Ta-dam. Ta-da-da-dam. Ta-dam. Z-score. So the idea behind it is that the z-score takes whatever number we throw at it, whatever x we throw at it, and what produces is produces a number that lies on our standard normal curve. So say we picked a number x that was equal to the mean. Right? We picked up the mean number. This means that the z-score would become what? Well, would become mean minus mean divided by standard deviation, which would become 0. Right? It works. Now, what else is cool about it? Well, the cool thing about it is if I asked you what is x, actually differently, what is z negative 1? No, z negative 1 means it's a value, right? Or a z-score, right? But also the value that is represented by the z, that is 1 standard deviation away from the mean, right? And I can even tell you that it's smaller than the mean. Which means that, for example, the empirical rule that said that 68% of data was within -1 and 1 standard deviation. Well, that's z-scores between -1 and 1 account for the 68% of the data. And again, I don't think I have to stress this, but 100% of the data is between -infinity and +infinity. Like you have to account for all the data. If you want to account for all the data, you have to account for all the data. Right? So again, mean of 0, standard deviation of 1, area of 1. Which means that z maps, in mathematics maps means is a function that does something. Maps normal distribution to normal distribution to standard the standard normal distribution. That's all it does. Okay. So z-score is x minus mu divided by sigma, and again important, x minus mu, not mu minus x. Mu equal to 0, standard deviation equal to 1, area equal to 1, and thus the greatest thing is area probability. All right, so how do we deal with this? Well, there are several ways we can approach problems like this. So for example, if I ask you what is the probability to select a student who scored 55 on an exam with an average score of 50 and a standard deviation of 2. What's the probability to select a student who scored 55 on an exam with an average score of 50 and a standard deviation of 2? Right? It's called grades are normally distributed. Now grades are normally distributed, but we want to convert those normal grades into standard normal. So let's see, we have a mean of 50, a standard deviation of 2, right? And we have an x of 55. Oh, then we can calculate the z-score to be 55 minus 50. Why? Because we're looking at z-score. X minus mu divided by sigma divided by 2. Well, that comes out to be 5 divided by 2, which means that the z equals to 2.5. We got a z-score. Now, there's several ways we can calculate the probabilities. I'm going to show you two, by hand and using an online calculator. And again, on the exam you're going to have to do it by hand, but for all the other work that you do, you can always use an online calculator. So by hand you do the following. First, after you calculate the z-score. So you need the z-score first. Second one, you draw the picture. What picture? Well, the standard normal picture. Again, artistic freedom. Middle is 0 because that's the mean, right? And mean is 0. Even though the mean here says 50, this is standard normal curve. That's important. So mean is 0. Where is 2.5? Well, 2.5 will be on the right side. Artistic freedom says about here. What's the probability? Well, probability is 0. Why? Because we are looking for one student out of a whole group of students, right? And we're back to this conversation. Okay. But if I say 55 or more, what is 55 or more? Well, 55 or more means I'm looking for probability of x being greater equal to 55, which means that I'm looking for probability of the z-scores being greater or equal to 2.5, which is this part. Now we can do this, right? So depending on what the question is asking is this. If I said you 55 or less, we will be looking at all this. So this is 55 or more, and right here will be 55 or less. Right, so the other side of the equation is 55. Right, let me pull up a Z-score table. All right, boom. So a Z-score table. The Z-score table has a couple features. One, it only gives you the area to the left of the Z-score. At least that's the standard Z-score table. There are some other ones that and one of those tables you can find in your packet of tables posted on the website. So only to the left. So in our case, this, if we looked up this Z-score, it will give us this probability, the red one, versus the black one. The good thing is those are complements of each other. So if we have one, we can figure the other one out. So let's take a look. We're looking at 2.5. So 2.5. Okay, so 2.5 is right here. Well, the question is why the hell we have all those other columns? Those other columns correspond to the second decimal place. So a pure 2.5 is right here. So it's 0.9938. Well, to the left, so this is 0.9938. Right, let me draw this picture again. So this area is 0.9938. This is all this. That's according to the table, which means that the probability for this section, well, it's a complement, so it's 1 minus 0.9938. So that probability equals to 0.0062. Oh, come on, guys. Right? So depending on which probability we're looking for, we have an easy way to find it. Right, let's do one more. Let's say the mean is 32.2. Let's say the standard deviation is 0.7, and I'm looking for values of x which are smaller. So than 3.1. Sorry, 31.1, 31.1, yes. Okay. And so how do we do this? This time around, I cannot be lazy anymore. I'll grab myself a calculator. So, what do we do? Well, we have to find the z-score first. So z-score equals to x minus mu divided by sigma. So in our case, it's 31.1 minus 32.2 divided by standard deviation 0.7. So 31.1 minus 32.2 divided by 0.7. And I get a z-score equal to negative 1.57. So we have our z-score. Now I graph my standard normal distribution. Again, I like to notch my 0 in the middle so it's easier for me. Negative 1.57, and we want values smaller, so we want this. We don't care about this, we just want this. Okay, well, let's look at the table. Negative 1.5 is here, and 1.577 is right here. So it's this number right here. 0.058. So 0.0582. So the probability for finding an x smaller than 31.1 equals to 0.0582. Done. Okay, more. Let's do more. How about if we have... Oh, come on. Sorry. Right, how about if we consider something slightly different? How about we consider the mean of 32.2 still, standard deviation of 0.7, but how about we ask for probability of x between 31.1 and 32.6. Well, how do we deal with this? Well, for that we have two values, so we need two z-scores. Z-score again is x minus mu divided by sigma. So for the first one, right, it's 31.1 minus 32.2 divided by 0.7, and that came out to be negative 1.57. We just did this calculation. And for the second one is 32.6 minus 32.2 divided by 0.7, and that comes out to be, ladies and gentlemen, 32.6 minus 32.2 divided by 0.7, and that came out to be 0.57. Oh, look at that, completely random and yet so pretty. Draw the picture. Well, so 0.57 is right here, negative 1.57 is here, and which area do we want? Oh, we want the middle part, right? We want between. So we want all this. So how do we deal with this? Like if it was below, we knew how to do it. If it was above, right, we took the complement. What do we do when there are in between? Well, in between is actually not that difficult because we just look at the graph and we can find this probability for this whole area because the table gives us to the left, and we can find the probability for this area. Right? So if we want to find the probability for the middle part, hence this probability minus this probability. Right? So in our case, this area, this probability for x, for 31.1 being smaller than x, smaller than 32.6, this area would equal, this middle part would be equal to probability of x smaller than 32.6 minus what? Well, minus this section, which is probability for x being smaller than 31.1. Right? This had a z-score of 0.57. This had a z-score of negative 1.57. Now let's look at this. 0.57, 0.57, right there, 71.57. So this probability equals 0.5157. Makes sense, right? It's slightly bigger than our mean, which means the probability should be bigger than 50% for the whole section. So this whole probability is 0.5157. Right, what's this? Well, negative 1.57. So negative 1.57, 0.582, 0.582. That's 77, yes. That's 0.582. So this is 0.582. And this is this section here, which is 0.582. So the big piece minus whatever the little piece is. Right? So this probability equals to 0.5157, which is this whole section, minus this little piece, which is minus 0.0582. And which comes out to be 0.4575. Which comes out to be 45%. Pretty cool. All right. 0.4575. All right. Well, let's keep going. So how do we have fun with this? Well, we could ask a very simple question. Considering our distribution, what number, what value, represents the bottom 10%? I want to cut off the bottom 10%, right? And here we get to this cool concept of finding a z-score from area, right? And by area I mean probability. So we have to work backwards. First of all, we need to know what this looks like. So we need to look at the picture, and that shouldn't be too difficult. We know exactly which picture I'm talking about, and so this should be relatively straightforward to do. So, draw the picture. Second one, we're going to use the table in reverse. Well, the table in reverse is what? Well, we're going to look at the area and find the z-score. So first things first, we're going to draw the picture. What's 10%? Bottom 10. Well, this is top, this is bottom, so bottom 10 is, say, here, right? This is 0.1, which makes this 0.9, just in case you wondering. Okay, well, so questions, what is this z-score right here representing this? Well, to do that, we have to go back to our table, and what we are going to be looking for inside of the meaty part of the table, which means right here, we're going to be looking for 0.1. We're going to be looking for this number, 0.1. Also, we have to be careful. We find 0.1 here, right there. Oops. So it's negative 1.28. So the z-score here is negative 1.28. Again, how do I get it? I find 0.1 right here because that's our probability, and then go negative 1.28. So this is our z-score. And then how do we find the actual value? Well, if our z-score equals to, then we can transform this through a set of algebraic manipulations into x equals mu plus z sigma. Well, so our x equals to 32.2 plus negative 1.28 times 0.7. Which comes out that this is corresponding to x equal 31.304. Right? Very easy working backwards. All right. Since I'm still talking to myself, still talking to myself, I'm gonna take a couple minute breather, get some more water, and then we'll continue. All right, that was a very enjoyable break. Fast coffee. So where were we? Ah, yes. So this is the basics of what we want to cover in chapter 3. The difficulty starts when we start asking questions like, what's the top 40%? What's the bottom 90%? Or what's the top 60%? When you start using those terms, I see a lot of mistakes showing up. Now, one can see that, for example, the bottom 90% will have the same z-score as the top 10%, right? The top 60% will have the same z-score as the bottom 40%. Now, why do I say this? This is bottom 60%. Well, because if we actually draw it, and on the final exam you will see, if you're in my class, on the final exam you will see a sentence on the first page saying, draw the goddamn picture. The reason why is I found that over the years, people that don't make it through statistics in my class are people that don't draw pictures. I know, sounds childish and you think you would be able to do it in your head, but little mistakes will creep in because of stress, because of whatever else. So I mark the middle, but that's for me. I find I work better if I have a point of reference. So I mark the mean in the middle. Again, the mean at 0, at 50%. This is the way it is. And now top 40. Well, top, I'm looking at this part, and we're looking at only 40%. So from the top, about here. This area is 0.4. Well, if this area is 0.4, then this area is 0.6. Same thing here, if I'm looking at the bottom 90, so bottom 90, I would expect to get this. But this is the same as saying, hey, bottom 10. And then top 60, top 50 is right in the middle, top 60 would be here. So this would be bottom 40. And the question is, which number are we going to be looking up? Well, we're going to be looking up the bottom one. Why? Because the z-table only gives you the area to the left of the z-score. So if you're looking for this z-score here, what you're looking for is you're looking for this area. Not right? Not this, because this is top. We're looking for the bottom, right? And here the bottom is this one. So regardless of which one of those you're given, if you're given the top 10 or the bottom 90, right? Regardless of which one I'm actually looking for in our questions, right? The questions are in red, the opposite. Regardless of which one, we're still going to be looking up this. Why? Because the z-score table gives you the area to the left of the z-score. So let's look at 60. Where is 60? 60, 50 is at 50 is at 0, 60 will be right here. between those two, this one's closer. So that's 0.25. Next one, we're looking up 90, and 90 shows up, that's 90%, and then it's 1.28. So this is equal to 1.28. And then the last one is 0.4. We need to go to the other table. 0.4. 0.4. This one, it's negative 2.5. Negative. One couldn't realize that because this graph is bell-shaped symmetric, then this and this should have the same z-score, just with a negative lying around. Right? So that's another clue. This area is bigger than 50%, z-score is positive. This area is smaller than 50%, z-score should be negative. Alright, easy enough. Alright, now we have alright, so let's talk about usability. And here's an example. Scooter gangs. Here's an example which I always like to give. So the example looks the following. We know that a lot of things about human beings are normally distributed. Heights are usually normally distributed. Weight is usually normally distributed. Besides that, size of heads is normally distributed. Most of the furniture that you see in stores is standardized. Tables, for example, the tabletops are about 30 inches away from the floor, because that seems to be working ergonomically better. Chairs are about 18 inches away from the floor. Again, why? Because ergonomically that fits. People like myself who are tall, I'm 6'4", sometimes that feels a little cramped. But on the other hand, people that are much shorter than me still find it usable. So let's consider the following, that when you drive a car, besides that fancy steering wheel of yours, right, and the blinkers, you have a whole console here. You have your radio station, you have your AC, you have your whatever other buttons lying around. And when you're sitting here, eventually you might want to, put your grubby hand on the AC. Now, there's your head and there's the other. Now this example ain't very fun. So let's make it a much more fun one. Let's consider the following. So if we consider my mother-in-law, and my mother-in-law is driving a car, right? So we have my mother-in-law driving a car. So if my mother-in-law is driving a car, right, and we have some reason that things are about to get really, really hot, and we have a meteor falling down. Well, the obvious thing to do, the obvious thing to do is, if a meteor is falling down, is to reach for the AC button, which is right here. right? So one would need to consider designing cars for T-Rexes. How far is this button, right? Is it reasonable? Can you reach to the side of it without, leaning, pushing one another? Oh, let's make it fancy. Okay. Right? So, if you consider this, let's consider the following. A grip reach for women is normally distributed. The mean is 27 inches with a standard deviation of 1.3 inches. Find the value for find the value representing the longest 95% of women in terms of grip reach. Okay, well, first things first, picture. Where's the 95%? Well, short, long. So the longest would be right there. So we're looking at the longest. But this z-score just separates the longest from the shortest 5%. So this is 5. That's z-score. Alright, if we look up the table, 5% ends up being right between those two values. Right, so that is negative 1.645. Now, here's a side note. For the most part, when we're talking about z-scores, we're talking about the closest one we can find, with two exceptions. 1.645, which represents 95 and 5% split, and 2.575, which represents 99.5 and 0.5% splits. These two z-scores, we use one extra decimal place and we round the middle part. Everything else, we just take the closest one. So if you look at our previous examples, right, we always picked the closer one we could find, with exception of those two. And again, we're going to be doing enough examples that this will eventually show up enough that we can, find it consistently. Right. So we have found the z-score. So now we find the x. Well, x is mu plus z sigma. So in our case, that's 27 plus minus 1.645. Mind you that on most calculators, subtraction minus and negative value minus are two different buttons. So you have to make sure you push the right one. Times 1.3. And that comes out to be 24.86 inches. So what does this 24.86 inches mean? Well, it means that if your arms are shorter, or your grip reach is shorter than 24.86 inches, use a shorty. That's all it means. It means that when we design cars, we are not worried about people having too long of arms. We worry about people having too short of an arm. And for that, we have a limit. And so 2.486 inches means only 5% of women, right, the shortest reach, won't survive the meteor, right? Right? If the grip reach is 2.486 inches. 2.486 inches. Right? If we can establish this to be this, 95% will, 5% won't reach. And again, I understand the whole idea of being accommodating for everybody, but eventually you need to draw some lines, right? And I don't know where to do those, and statistics allows us to have a very clean kind of number that we can deal with, and that's right here. All right. I hate scooters. And this example concludes chapter 3. I will be posting some practice problems online, so you can keep on fighting with this, but that's about it for discrete and continuous random variable. Next up is sampling distribution, which I will start after a quick break. I'm gonna start it in a new video, so just look up for that. All right, thank you.